Hello everyone, this is a AL60 cryo cooler. This is a GM cycle or Gifford-McMahon cycle cryo cooler. It uses helium to generate cryogenic temperatures at the cold end, which is over here. This is normally also called a cold head. You have helium input, which would be this connection here, and then your helium out right here. And usually the high side's around like 290 psi, low side's around 50 psi of helium. The helium that it goes into this is very pure, usually 99.995% or higher, with a very low moisture content and also oil-free, since any oil that would make it into the cold end would just freeze and probably would cause some pretty bad problems. These are normally used in a cryogenic crystal cooler. The crystal cooler would generate a cold flow of nitrogen gas that would allow you to freeze crystals and I guess do some analysis of the crystals, or maybe cutting, or at least some type of analysis. Not very sure what they do with that. All I really care about is these cold heads that come from them, because they are pretty good. They generate about like 80 watts of cooling at the cold end at 77 Kelvin, which is liquid nitrogen temperatures. These are also driven with a AC power source for the actual valve actuator inside. It's just a little stepper motor running at 120 volts with a capacitor, resistor, a dropper across the third phase to phase shift that, so that it'll rotate in the right direction, but also run that motor off of a single phase source. This one here, it does weigh a good bit. It is very well constructed. I just did cut it off of the actual vacuum flask that was here. This had a vacuum insulated container around there so that these cold temperatures won't really leak out and be warmed up by the environment. There's still a little bit of mylar and insulation here. I'm going to go ahead and remove that, and we'll go ahead and tear this thing open to see what's inside. There is also a pretty common failure that I found in a couple of these where the actual motor mount screws are very short, and either they unthread themselves or they strip out, which can back off and damage the actual rotary valve in there. The actual displacer, there's a displacer in here that moves back and forth, that moves the helium from the cold end to the warm end during either when it's compressed or when it's expanded. That displacer is all operated pneumatically in here just by the helium gas. But let me go ahead and start removing some of this insulation here to get inside. Just to expose this, because we don't really need the insulation anymore, since we are not using it in its original configuration. Okay, so this is the actual, showing the actual cold end here. There's the cold finger, which is right here. It is very shiny copper. Won't be very long once the oxidation starts happening. This was in a vacuum, so there is no air or any contaminants that would have allowed that to oxidize, so that's why it's in a very good condition. It looks like they used some type of brazing rod that is probably maybe nickel based, that allowed them to attach this copper to the actual stainless steel. The normal flow of nitrogen gas that runs through here would be through this inlet port here. It would actually work its way down to this is just a little cavity. It's really for if any liquids would be produced in here, like liquid nitrogen or any other type of non-condensables, or not non-condensables, but like ice, because the nitrogen source, it is usually site generated just because of the amount of quantity of nitrogen that this thing would use. So there might be a small amount of moisture that would freeze out in here, because if it freezes up in here, which is where the heat exchanger is, it would just plug it up and it won't really function anymore. But the nitrogen would go in here. It would then go through a small network of tubing in here and out through this little pipe. And there's usually a vacuum hose that comes off of here with a dispenser that would control that temperature by mixing in warm nitrogen gas so that they can have a specific temperature of gas that's going onto their sample. It's very, it's pretty simple internally. Of course, if this thing were to turn on right now, this thing would just start making liquid nitrogen right here, just dumping it all over the place. It's about 80 watts, so at full capacity, this would probably do about 10 liters a day. And so therefore, it does generate a pretty decent amount of cooling. But let's go ahead and look here. So these are the actual AirEquip quick disconnects. These are for the helium supply and return. The high side, of course, works at 290. The low side is around 50. These are self-sealing quick connects. They are designed to be very low, loss when you disconnect them, but they also prevent any air from entering as you connect them. There's very little space in there when you're actually putting the connector on, so that there's very little impurities that get into the system, because impurities would just mess up the system by either, if you have like nitrogen impurities, it would just either condense inside of the actual cold end, inside the helium side, which could be pretty bad, or if there's any water or contaminants that could also freeze and prevent this thing from operating properly. Let's go ahead and I'll go ahead and take off the back end. This will be the actual valve assembly right here, and then we'll go ahead and take a look at that. So the back end of this is just held together with Allen head screws. They are countersunk in the back here. Let me go ahead and remove those so we can go ahead and take apart the actual unit itself. Okay, so it has come apart, and I guess one important thing that I have not mentioned is you should depressurize this. There should be probably about 210 psi in here if it was just disconnected from the helium compressor, and if it was up to that pressure, which is the standard standby pressure of these systems. So I previously depressurized this. I got an adapter that allows me to connect and use a little ball valve to depressurize this. So here is the actual valve assembly. And then this is the actual displacer assembly here. Here we just got a simple O-ring here that keeps the helium in. Helium is a pretty small gas. It's actually the smallest gas since it is monatomic, unlike hydrogen, which is diatomic. And it just leaks out of everything. But these seals are specifically chosen. I'm not sure what type of material, maybe nitrile, or I'm not sure, but it's specifically chosen to prevent that helium leakage over time, or I guess as it permeates through the whatever material that is. So let me go ahead and take apart the valve assembly. It'll be right here. It's just going to be a ceramic rotary valve that it's a oilless type system, so it's just very smooth, high polished surfaces that do all the sealing. I can find the right size here. Okay. And I got the gloves on because nothing's really toxic in here, or there's nothing really, that's dangerous. It's just I don't want to get any oils or anything on here, just because I do plan on using this actually pretty very consistently, and I want the hours out of it. These things are not very cheap on eBay, and they are kind of hard to find. But every once in a while you do find one that actually is pretty inexpensive. And I've collected a couple of these. Actually, this is my third one, and I'm able to produce a pretty decent amount of liquid oxygen and liquid nitrogen on site. Which is pretty neat to do. There's a lot of fun things you can do with definitely liquid oxygen. So let me go ahead and pull this guy out. It should just slide right out. Got a little trouble here. I'm gonna try using 2 Allen wrenches. Just gotta be very careful not to damage anything. Oh, there you go. So this is the actual bottom plate here. This has the channels for where the helium, there's a little bit of dust in there just from previous use, but there's little channels that actually direct the flow into the actual cold head to move the displacer, but also to actually pressurize and depressurize the actual expander section on here. So here is just the plate. It's very, very highly polished because there is a ceramic valve here. This valve just rotates. Not sure what the RPM is. I mean, actually, if we pull the motor out, which would be kind of difficult because of the actual connector, the wires are not very long, and I don't want to really mess with this because another potential helium leak could occur if I mess with that. And helium leaks are pretty hard to find when they're really small, and it's not very good to have to keep topping up a system with helium just because it is the industrial or higher grade helium, not just something you can go buy at the store very easily. So here's the actual rotary valve. It rotates on this plate here. Either connects both of these channels to the center, or it connects this channel to the center. And then also it vents the either these channels to the cavity in here, or it vents this channel, which would most likely be for your displacer. So here's your actual rotary valve. It should just pop right out. There it is. It's a square drive off of the motor. The good thing is it looks like the Allen bolts which hold the motor on are still there, though I will probably take them out and either put some longer ones in because the actual bolt holes in the motor are longer, but also because I've seen that at least twice where those will back out and start being chewed up by the back end of this. I mean, it can create some dust and therefore mess up all these high tolerance components in here. But the valve itself looks pretty good. I mean, there's a little bit of just dust probably from the absorber. The absorber in the helium compressor just removes any oil that is possibly in the helium because any oil in here will just freeze out in the cold head, and that would be very catastrophic. It would just kind of start seizing it up and possibly damage components in there. So here is the actual back section. The actual helium, the high pressure helium, goes to the cavity. So this whole cavity of the motor is under pressure, while this ring here with this little port is your low pressure return side. And that would actually be connected to, on this guy here, it would actually be connected to this port here, which goes to your center. So your center is actually your low pressure side. And so therefore the high pressure would make its way in here or in here, depending on the orientation, or it will vent the helium from here or the displacer drive actuator to the center and allow it to actually oscillate. This thing, of course, it runs about, I guess, a little bit faster than 1 time a second for operation. So since this is doubled up, this is probably going at half rotation per second in order to make that drive. So let me go ahead and pull the back side of this off. I mean, there's just going to be an O-ring in there. It is kind of actually harder to do usually because it's actually recessed in there. Well, I guess maybe I shouldn't take that off because I mean the thing is that it's recessed and there's an external O-ring that slides into a cylindrical hole, and therefore I mean taking this off could possibly roll that O-ring or damage it. And since there's nothing really wrong in the actual here, the motor's end, we'll just leave that in there. I mean, I'll try one more time, I guess. Well. I mean, just believe me, there's just a motor in there and some 3 wires going to this connector. I'd rather not damage this. I mean, there's really nothing wrong with this. I'm just really wanting to make sure that these bolts are present or actually in their hole. And what I'm going to do is put some Loctite on there just to make sure that there is no possible way that they will back out on their own. I mean, I guess Loctite isn't 100% all the time, but I mean, if you use very small amounts and let it cure before you actually put this in operation, it should be fine. And I mean, before this thing can even function again, You have to pull a very good vacuum on this. I have a pretty decent sized vacuum pump, it's 3 horse. I'm not using a turbomolecular pump or a oil diffusion pump, but I can usually purge enough helium through here to, and also cycle it to make sure that it's pretty much nothing but helium in here. I do pull the vacuum for a decent amount of time to make sure any moisture that does accumulate during the opening of this to freeze and then sublime away, but it's just you really don't want any contaminants in here because it could mess something up pretty easily. But this is the actual, just the motor side, the valve, and then here is, of course, where you're actually, the helium actually enters the actual cold head itself. So let's go ahead and pull that little valve block out. This is just where all the helium kind of goes. Actually, there is a screw hole to pull that out. Let me go find a threaded screw or bolt that will fit through that and allow me to pull it out. Okay, so I found a screw that mostly fits in there and actually allows me to pull that out. So let's go ahead and thread that in there, just a few turns. All right, we're gonna go ahead and pull it out. So here it's coming out right here. There's no real gaskets in here or anything, just because this is all in the pressurized helium. I mean, it's already protected by that seal there. So this is the actual, one of the actual drive actuators that moves the displacer. It's just a hole with a seal in there. That seal seals around a, I guess you could call it piston, that when pressure actually enters the center point, which would be this hole here, it will then put pressure behind this to shift that displacer downwards. So you got 2 center holes here, or they're offset. These holes go to the back of the displacer. They are for the helium to return and also be added to the expander side. So this is just constructed fairly simple. It's really just mostly aluminum here with a little bit of some type of probably plastic. And then there's of course some type of special seal material in there, or I guess a external piston ring of some sort. So in here is going to be your displacer. We're going to pull that out. There is a thread hole on top, but this should hopefully just slide right out because it's just a very high tolerance. So here's your actual piston. This piston operates through this little, or is it the cylinder here, and this is what actually pushes that displacer down. We have a wave washer or a spring. This is because this displacer is moving up and down to move that helium from the top side to the bottom side. And so it does impact each side, and you need something to absorb that impact. It looks like they have stacked 2 spring washers in there. And then they also have these, I guess, wear rings that allow it to slide very easily in there and prevent actual, damage to the wall, and also centers this as it's moving up and down. It also does seal a little bit too, because the helium itself does run through inside the actual displacer. So, because there is a regenerator inside. So here's the actual displacer itself. A little bit of discoloring here, but that's just because this thing has quite a bit of hours. There's a little bit of buildup on here, which I will clean. This displaces the helium from the warm side to the cold side, which is cold side here, warm side here. There is a piston here that does ride inside of this, which is the actual cylinder for it. There's a seal in there, and it just works its way back and forth. The way it works is pressure is pushed on the backside through this little hole with an O-ring groove around it, to push this displacer over. Once the displacer is over, the helium moves to this side, which is allowed to be compressed. When the high pressure helium, the 290 psi helium, enters this area, it is compressed. And then when pressure is relieved from here, the pressurized helium in here is able to push this displacer over, because you got the area of lower pressure behind the piston, and therefore this will actually shuttle back over, moving the helium through the displacer out through this tip. This tip here is actually going into a seal that is at the bottom of the cold head, and it pushes that helium through a mesh of copper. It's like very finely machined copper, which I'll show you a picture here. And it allows the helium to get good thermal contact or thermal transfer to the actual cold head. Helium is it does have a decent amount of thermal capacity, but also it's pretty hard to actually transfer the heat to the helium. So therefore, that is used to help the thermal conductivity of the energy from the cold head to the helium gas, since you do want to actually cool that helium down. All it does is that helium moves through here. Once it is in the cold end, it is expanded, which allows it to cool down. That helium in this chamber here, so the helium works its way through, goes through the mesh, and then comes out into this little cavity. It's expanded, and as it expands, it then has to work its way back through that mesh and into and through the actual displacer, and that will then cool down the actual regenerator in here. It is something that stores the thermal energy, or the lack of thermal energy of the helium gas. And so therefore you can get some really cold temperatures here, and as you go through that regenerator, it's actually pretty much ambient temperature up here, which is pretty crazy, 77 or below 77 Kelvin here, because this is at 77 Kelvin, and the helium actually has to be a bit colder to transfer heat. And then up here, it's pretty much above ambient, maybe 85 degrees Fahrenheit, or even a little warmer sometimes, depending on the actual helium temperature conditions going into here. It actually works really well, and that's pretty much how this whole system works. Is it just moves helium from the hot end to the cold end, and expands and compresses the gases depending on where that helium is. And it's all about trying to transfer that cold or the heat from the cold head to the actual helium gas, which should be really cold, and then we'll exit through the outside to the helium compressor. I guess one thing is that they use helium gas as a refrigerant, or the expanding gas, because it's very stable. It's almost like an ideal gas. You have to cool it down to like 4 Kelvin before it would actually liquefy, which is really, really, really cold. And this thing, of course, works at a little below 77 Kelvin. And so the helium is it acts just like it is, but just a lot colder. Of course, it's a little denser because of the cold temperatures, but that actually does help out with the heat transfer in the cold end, because you have more helium gas down there. So I'll go ahead and start reassembling this thing. I'm going to go ahead and put the displacer back in, but let me go ahead and finish cleaning out the actual bore of this. I'm going to use a microfiber cloth just to clean it out, and then I'm going to use very dry, clean compressed air that I have on site to blow it out and make sure there's no dust or lint or anything left behind, just because lint is not really that bad at warm temperatures, but when really cold, I don't know, maybe it might be a little more abrasive or so. I mean, even if it was warm, it'd still be a little abrasive. So I'd rather not risk that with this. So let me go ahead and finish cleaning this thing out, and then we'll go ahead and start reassembling it. Alright, well, I went ahead and cleaned out the actual barrel. I've flushed this out with compressed air both ways. The inlet, of course, is these 2 holes here, and then the outlet, of course, is through the very tip of this little piston. This is all cleaned out, and of course I cleaned all the dust off and everything. There's a little bit of dust that does form from these little wear rings over time, but it was very minor. And then I went ahead and took out each one of these screws one at a time so we don't drop the motor, and put some Loctite, just red or blue Loctite on there. And of course, when I do assemble this thing, you have to give it some time for that Loctite to dry. Then once that Loctite dries, then you can pull a vacuum on this and then start purging helium through it. So let me go ahead and reassemble the displacer. It should just pop right in.
Should
just move very smoothly. There's the actual cylinder for the piston on the displacer that moves the displacer back and forth. This does matter, well, it does kind of matter how you clock this, because when you do assemble it back together, you might want this in a specific orientation. Of course, there is only 4 screw holes, so it can only be in 4 orientations. So you do have to actually put this in where it is clocked right. So the way I usually do it is first go ahead and reassemble this end. There is on here, there are 2 holes right here that actually index with this, and then there's 2 holes for the heads of the screws that will index with this. So really this can only be in 2 orientations to actually line up with the actual bottom end for the top end. So let me go ahead and put this little valve on. There's just a square drive, so you just pop that right in there. It doesn't matter about orientation or anything. So that's the actual valve assembly. We'll just make sure that's perfectly clean. Looks pretty clean to me. Then we have the actual block that the valve rides on. I mean, looks a little scratched up. I mean, there's very minor surface wear on there, but I don't really see any actual like deep grooves or anything, and I don't see any dirt or dust that would cause it to fail. You do have to line up this. There's a little hole here for your low pressure side, and there is a hole here which allows that low pressure to go to your center of that hole. So let me go ahead and line those up. And of course it lines up the other screw holes too as you do it. Okay. In order to get that in there, we're going to go ahead and put the 2 screws in and rotate it until it falls into the holes. There it is. Go ahead and tighten both of them. All right, so that's all tight and everything. There is a O-ring here that operates, or that connects that hole to the O-ring. That actually needs to be, placed in here. There's a little groove for that. And that, of course, operates the little piston that moves the displacer back and forth. So we'll go ahead and line that up with that. So there's only 2 ways because of these holes here for the heads of these screws. And you just need to make sure that, of course, that O-ring is lined up with it. So let's go ahead and put that there. Okay. So the whole entire assembly is together. You could put some grease on here. The only grease you can really put is high vacuum grease, and a very small amount, just because you still don't want the grease working inside, but you need that grease to have a very low vapor pressure so that we don't have any contaminants that make its way to the cold end and start causing some issues down there once it freezes. So we'll go ahead and put the actual the cold end back onto the actual valve head assembly, and really there's 4 positions it could be on. It doesn't actually matter what's position, other than you just need to have this coming off of a decent side that doesn't affect how you're going to use this thing. And for me, I mean, I'd rather just come off to the side where I still have access to both of these ports, because I will be putting this will be a pressure measuring port, and this will be the actual gas going into for liquefaction. So let me go ahead and assemble this. Just let me make sure that this is really clean. All right, we'll go ahead and insert the bolts. Okay, I'll just get them all kind of seated in there. Alright, so that's pretty much this whole displacer. Put back onto the actual, I guess, the rotary valve head. And so the next thing is to let that Loctite dry. I mean, there's very little of it in there, but I still want that to dry because it could contaminate the system. And then what I'll do is go ahead and hook up the vacuum to the, well, I usually do it onto the return side, though it does have to work, all that gas has to work through that little mesh in here and through that rotary valve in order to pull vacuum. So you do need to operate the valve a little bit, and that will, you know, kind of cause the gas to get purged, or all the gas to be purged out. And then I usually add a little bit of pressure of helium here, pure helium, while still pulling a vacuum and also operating the valve, so that it will then pull all the contaminants out and purge it with pure helium. And then usually I then close this valve, let this build up to about 210 psi, which is the rated standby pressure of the system, and allow it to then sit, and then pull one more vacuum on it while purging some gas through, and then bring it up to 210 psi. Then disconnect the lines, and it'll be ready to be installed into the system to then do what it needs to do, which is to generate really cold temperatures here, about 77 Kelvin, to liquefy any gases that are present, which should hopefully either be nitrogen or oxygen, and then also do that at a considerable rate. These, of course, do about every 24 hours, they can do about 10 liters of liquid oxygen, or about 2.5 gallons-ish of liquid oxygen. And it's about the same for nitrogen too, about the same, even though, I mean, they're not exactly the same, but I just consider it 10 because it is a pretty decent amount, plus or minus a percentage, which is, of course, depending on your helium inlet temperature. Usually the cooler the helium coming in, the more effective these are at cooling, and then also just other conditions of how the compressor is running and how well the helium is transferring the thermal energy out of the cold end. But you know, these are pretty robust. They're pretty simple. Of course, you do have some pretty exotic parts like a ceramic rotary valve, which of course they do have them in sinks and stuff. But if you ever had to get another one of those parts, good luck. I guess you can call Rigaku, which is the manufacturer, and see if you can get a part, but it probably won't be very cheap. Just because it's a very specialized part for this. And then also you get the displacer, which, you know, the only thing that could really go wrong is if you get contaminants inside that displacer that will plug it up or prevent heat from being transferred to the regenerator that's inside the displacer, or if you also get contaminants that actually plug up all those little holes or mesh network of copper at the very head. You won't get very good heat transfer or even helium moving through the system properly. And then there's some wear components such as those rings, but I mean, the rings at the bottom, yeah, they are pretty chilly. So there could be a lot more I mean, they are designed for it, but it could wear away the aluminum or stainless housing or wear the rings themselves away, which I'm assuming the rings are softer even at these cold temperatures than the stainless, so that will be the wear item, not the actual cylinder itself. But let me go ahead and let this thing kind of sit for a little while. We'll let that Loctite, which is just the blue Loctite, to finish, curing or drying. And then I'll go ahead and start pulling the vacuum on it. And usually I try to pull it down to a pretty good vacuum. I mean, I don't have a turbomolecular pump or a diffusion pump, but I am able to at least pull it pretty low to where I can flush enough gas through here that I'm pretty confident that it's pretty much pure helium, no water, and no other contaminants that could possibly cause issues in the system.